Morning, everyone. Welcome to day 3. So we'll get started now. Thank you.
Thank you, Christy. Good morning, everyone. So welcome to the first session of the day. And this session is going to be on solar science. I would like to welcome Divya Oberoi to give his overview of solar physics activities with the MWA. Okay, go. Thank you so much. And it is such a pleasure to be here. Last time I was here at an MWA meeting, that was the 10 years of the MWA. So happy to be back here and, preparing. Okay, yeah, this is the outline. Because there are a lot of, I think, new faces in the audience, it would be perhaps useful to talk a little bit about what is the nature of this solar radio emission, which makes it, so challenging. And then what can you learn about solar physics from the various radio probes, right? Both the sun and the heliosphere a little bit. And then I'll give you a brief overview. I'll leave the details to the talks which will follow, and then I'll summarize. What I wanted to start with was to say that, preparing for a talk like this is a little bit of a trip down the memory lane. And it's sort of, I realized that I am perhaps now the person who's been associated with this project consistently for the longest time. I think this is even before LOFAR and MWA split. That was, our first, that was mostly from the NSF proposal for what we wanted to do for, solar and heliospheric science way back in 2004, site survey for the 32 tile system in 2007, and the first publication ever to come out of the MWA 32 tile system 2011, right? From there, it is very satisfying to see that this is where we have reached. And what is also very interesting for me is to see that, that orange curve at the bottom talks about our publications which come from instruments other than the MWA. So what we have been learning from the MWA, we've been applying to a few other instruments. Also, there have been natural reasons for us to extend our science, which requires us to go to maybe instruments with longer baselines like the GMRT and LOFAR, and to higher frequencies like the MeerKAT. And in all of those places, we are really charting, new ground. The first 2 solar papers from MeerKAT are from our group. The first 2 solar papers from the upgraded GMRT are from our group. For LOFAR, we've improved the solar imaging performance by more than an order of magnitude in terms of dynamic range. And all of this is really thanks to these people, right? There have been a bunch of PhDs which have come out, I think 6 so far. There are another 3 who are pursuing their PhDs using primarily MWA data, and there have been a few master's students as well. And so this is, solar radio people are a very small community. The guys with stars next to them are people who have now got faculty positions somewhere or another at a very prestigious Indian university or research institute. And so our community is growing, and we have always been limited by the number of people who can pursue the science and not by what the telescope or the data allow you to do. So I think it bodes very well for us to go ahead from here. Okay. So to tell you about solar radio emission, the top, that plot there, actually it was made by Randall a very long time ago, but it's a fantastic illustration of what I want to show. See, on the x-axis are labels giving you frequencies of 2 coarse channels each. Y-axis is time, half a second resolution. And what I want you to notice is that this emission is organized in terms of fibers, right? I mean, there are things which last for a very short time. There are things which don't last for too long across the band. So there are, if you can see, things like this, right, or these, which change quite dramatically across even a few tens of megahertz. They come and go very quickly. All of these are non-thermal emissions, and this actually comes from a time when nothing was supposed to be happening on the sun. So even for the quiet sun, there is a lot of structure in the frequency and time domain if you look at things. And the beauty of MWA is, of course, for every pixel on this plot, I can make an image, right? I end up with 500,000 images in just 5 minutes if I was to actually do that. Fortunately, I don't have to do that because not every pixel is independent of the adjacent pixel. So I can just sample it critically and do that. But the point remains that I have to image at very fine time and frequency resolution. The other thing which I want you to notice is this. The red boxes give you the brightness temperatures of these various well-known phenomena on the sun, different kinds of bursts, the quiet sun and CME gyrosynchrotron. And the blue boxes give you the degree of fractional circular polarization. So the brightness temperatures can go as high as 10 to the power 13. The fractional polarization can be from less than 1% to close to 100%. So basically you're dealing with a system which is, very structured emission across small time and frequency scales, rapid changes in morphology associated with those changes in time and frequency, spanning 9 orders of magnitude in intensity and 2 orders of magnitude in fractional circular polarization. So if you have to deal with such a system, you have to make really good images so that, a lot of these guys coexist. When a CME is taking place, this gyrosynchrotron is usually happening alongside a type 2. So if I want to see both of them at the same time, I need to have really good dynamic range to be able to see them. And what makes it possible, right? This is, I don't really have to say anything to you about this. What is really making it possible for the MWA is this fantastic dense UV coverage. We have a small footprint, lots of tiles that allows you to capture the information very quickly, monochromatically in a snapshot. And that is the secret for, our imaging quality. That is what we have been building on. But as again, all of you know, the imaging is can be quite challenging. I don't really want to walk you through the flow chart. All I want you to convey is that the algorithmic aspect of how to get from these visibilities to fantastic images, that we very much have under control. We have good implementations as well. It needs a little more work. We have never really implemented it till now on an HPC because we only got access to our first HPC comparatively recently. That's what we are working on. The computational challenge is really is an issue. That is something which we are, still trying to deal with. But basically, whatever would have been in our control, that we have done a good job on. And where have we reached with that? This is a comparison of MWA and various other solar imaging facilities, some of them dedicated, some of them, not dedicated to solar observing. And you will, on the y-axis is a measure of, the RMS in the image, or the darker boxes are the maximum, is the dynamic range which you would compute if you were to look at the deepest minima as the source of the error or estimate of the error in the image. So we are doing, a couple of orders magnitude better than others in the best of circumstances. All of these, I believe, are also best of circumstances, which people have quoted here. So we are doing extremely well in that sense. Now it's easy to imagine if, this is the sort of imaging which we can deliver, you're naturally going to open up a lot of phase space which has previously been unexplored. Simply not possible to get into because you never had the dynamic range to see it. And yeah, okay, I should have updated that number to 45 now. Okay, to give you a very quick sense for what all can you do with radio, right? Let's start at this end. In 1950s, from here in Australia, the solar radio bursts were discovered from type 1s to type 5s, right? Those are the sites of particle acceleration that, gives you information about the shock physics, the topology of the magnetic field, the electron beams which are traveling along these magnetic field lines there. And if you were to look at, if you were to go to higher frequencies, you can use that information to do what is called coronal magnetography, where you can sort of, again, a little bit of like layers of onion, different frequencies. The gyro resonance becomes bright at different magnetic field strengths. So by dialing your frequency up and down, you can figure out the magnetic field at different heights. For the quiet sun, it is the thermal emission. That's what we are mostly seeing from the solar corona, which is naturally sensitive to the electron density and temperature. That's another onion which you can peel and get information of the structure of electron density and temperature distribution. Because of the presence of the magnetic field, this is now a birefringent medium. If you are very good at detecting weak circular polarization, then you can also detect the average magnetic field, which might be there in the corona. And we have also been able to use our observations to, investigate some aspects of coronal heating. Now, all the radiation which is born in the corona is naturally propagating out through the corona, which is an inhomogeneous turbulent medium. And that gives you, a very beautiful probe of those propagation effects give you a probe of the nature of turbulence and inhomogeneities in the corona. And this you can do not only for coronal emissions, but also for IPS, as Angie will tell you. Now, all of this is really close to the sun, but as you go further away from the sun, the solar corona itself becomes too faint to be able to see. But the propagation effects it leaves on the radiation which passes through that, those are all still easy to see. And that is where, okay, I'm pointing to the wrong place. I should probably talk about here. That's where you can measure the Faraday rotation of background linearly polarized sources, which you are seeing through this corona, and get magnetic fields of CMEs while they are much further away from the Earth, right? And then, where is this? Okay, sorry. And this is about the interplanetary scintillation, which allows you to explore a very large part of the heliosphere, right? And that's something which John and his group have been pursuing here. And of the various things which I listed, the ones in green are the things which we have already demonstrated. The ones in yellow, there is a lot of progress which has been made on. And you need to go to higher frequencies to see that. And we have, while there has been work from the MWA group looking at the ionosphere, it has typically not been in context of the impact of solar activity. So that is something which we are yet to do. But there's a lot of it which we have actually been working on. Wow. Okay. Okay, this is going to be a busy slide, but this is central to what I want you to learn from my talk. On the x-axis is the frequency at which the emission arises. If your emission mechanism is going to be plasma emissions, which are actually at the local plasma frequency or its harmonic, that is what is plotted by the dark line. And the nu tau equals 1 is the height in the corona where the corona becomes opaque to its own radiation. Now, with the MWA, this is the frequency range which we are probing, and that tells you that the corresponding height range to which you will be looking at, if you're looking at thermal emissions or plasma emissions, is there. If you expand yourself to other emission mechanisms like gyrosynchrotron, we have seen solar emissions out to about 8.3 solar radii. Now, one of the things which is essential about solar radiophysics is that you need other sources of information as well to make sense of whatever is happening there. And one of the most useful ways which people have found are these coronagraphs. Now, the currently operational coronagraphs, that's where they operate, right? This is Core 2 and Core 3 on the SOHO spacecraft. The other source of information people have is images which you make in the X-rays and EUV, and their fields of view barely extend beyond 1.2 solar radii. So the place where we are really working, there is nothing which you have available to you to compare against, and that has been a big sort of stumbling block for us. That is now changing with the launch of this satellite Proba 3, which was launched late last year, and I'll talk a little bit more about that. There's another very interesting instrument which relates beautifully to the work being done towards IPS, which is called Punch. Now, we have also been, like I said earlier, expanding what we are doing to other radio telescopes. And now this is what we are able to do. If you were to look at the frequency coverage corresponding to all of these guys, we are now sitting from upper chromosphere all the way to about 10 or so solar radii, or go to 100 or more solar radii if you were to include IPS, right? So this is where we are doing our imaging. This is that heliopolarimetry. That's a term which John is really fond of, and I also like, which is about looking at the rotation, Faraday rotation of background linearly polarized sources, and then there is the IPS, right? So solar radio observations allow you to go all the way from the chromosphere to essentially the doorstep of the Earth, right? That is really the beauty of these guys. These are just what you're going to hear later today. So lately we have been, after having done, I think, a good job of Stokes eye imaging, we shifted our attention to polarimetry, and that's where we found some, interesting and unusual or unexpected things. That's what you would hear about from Soham and Pooja later today. Now, solar activity is inherently unpredictable. So if you want to improve your efficiency of observing, you need to figure out a way to trigger. That's what Deepan will tell you about. And some of the stuff about how we have improved our calibration is what Devajyoti will tell you. Proba 3, I just wanted to spend a word on that. This is, we are running a coordinated observing campaign between Proba 3, MWA, and the GMRT. We have 3 remaining epochs out of 10, but we have not met success yet. This is a fantastic formation flying mission. There are 2 satellites, 140 meters apart. This guy is the occulter. This guy is where the observing instrument is. You have to fly them with millimeter precision, millimeter and arc second precision for it to cast its shadow exactly on the the slot where, where you have to occult the disk. And it is expected to give you exceptional signal quality. This is one of their images, but unfortunately, our observing windows are yet to overlap, despite our best efforts. Yeah. Okay. I am really running out of time, so I'm actually not, okay, let me say just something about that. We have too much data and not enough capacity to analyze that. Some of the first steps we are taking towards that are being enabled by this NASA grant, where we are going to image 80 hours of MWA archival data. This is how we want to, this is going to be just 2.5% of what we have in the archive. But this is going to enable us now to get an HPC implementation of what we need to do. And we have, this is what is underway right now. We have already ways of figuring out overlapping radio events and so on. Okay. This is how we think of our data, because the objective of this data is to organize it as a machine learning ready archive. So we think of our data as a sort of 5-dimensional cube. I mean, if you were to look at the image, of course, there are the 2 dimensions, but for every pixel here, I have time and frequency and the 4 Stokes parameters. That is really what we want to present to this machine learning archive. And then let's see what comes out of that. We have a lot of data in the archive, but Sun is a very unusual source where old does not necessarily imply useless or low priority, right? In fact, MWA is the only instrument of its capability, which has an archive spanning a solar cycle, right? So we are trying our best to try to maintain or preserve as much of that data as possible. It has also happened that in the past decade or so, there are many other independent observatories which give you these complementary information about the sun, which make it a whole lot easier for you to extract physics from these. So for us, it would really be a tragedy to lose these sort of irreplaceable data. But of course, we understand the need to do something to make space for more data to come into the archive. Here is some of the stuff which we want to do. Some of these are discussions which are already undergoing. Simply spectral averaging to 160 kilohertz gets you to 1/4 of your original volume. It's a lot of effort to take it out, do the averaging, push it back into the archive, but that's one possible way. We are working with a colleague in Bulgaria to try to move some of the data there. And Richard Dodson had some thoughts about how you might compress, but I think it'll take some more time before we can go down that route. Lately, we have been observing with very low duty cycles, right? 2 minutes per 30 minutes to sort of get a good sampling of what is happening in the day, but not gather too much data. And also we have been following triggered observing to, concentrate our observing where really it is interesting. The other thing is all these images which we want to make, we want to make them publicly accessible via the virtual solar observatory. And the pipelines which we are making, we also want to make them public, because we will probably not have the compute resource to image most of it. But if you have the pipeline, if it is easy to use, maybe if you need it, you will be able to do that. Last things I wanted to say is that we are a small team with rather unusual needs and requests. And also we're sort of not that plugged into the MWA community because physically we are not here. I owe most of my career to the MWA team. So I really want to thank the project for having delivered whatever it has and all the support it has offered. So in summary, all I want to say is that we are really well poised to continue to reap the science results from all the effort we have put in building our ability to calibrate and image. The science applications span a very large range. I've already given you a sense for that. We are working on scaling up our processing and successfully applying the lessons which we have learned from MWA to other SK pathfinders. And with that, I'll stop and take any questions.
Thank you so much, Divya. So we have less time for the questions, but
apologies for running over here.
That's okay. Any questions from the room?
Thanks. Great overview. In your introduction, you showed the different classes of solar bursts. And historically, that classification was very important because our understanding of the mechanisms followed once we had a classification. Now, my question is, when we go to extragalactic systems, pulsars, FRBs, everybody wants to assume there's only one emission mechanism. It's a false application of Occam's razor. But why is it that when it's so clear in the sun that there's more than one mechanism, people don't seem to accept this for outside the galaxy.
Okay, well, that's a hard one for me to answer. Yeah. But I mean, I appreciate what you're saying. And in fact, what I now believe is that even for the sun, this classification we made into types 1 through 5 was really an artifact of what the instrumental sensitivity was at that time. If somebody was to start afresh and do a classification now, you would come up with something different. And for what I believe now is that what you will come up with is really a measure of the sensitivity of your instruments. We see so much stuff happening when everybody says it's quiet. So it's not really an answer to your question, and I really don't know. Even for the sun, I think we are fighting that it is not always plasma emissions here. There are other PCME and other things which are also at play occasionally. So, sorry, no good answer to that here.
One quick, we can just take last one, if you have any. I don't think so. Okay. Thank you. Thanks
so much.
again, Divya. And the next one is going to be an online presentation from Deepan Batra about enabling real-time triggered solar observations for SKLO, a demonstration using MWA and Yamagawa. Hi, Deepan. Would you be able to
Yeah, can you hear
share
me?
your screen? Yeah, we can hear you.
Yeah.
Can you share your screen and
Yeah, I am doing that.
presentation? Yeah.
Is it visible?
Yeah. Yes, it is. Yeah, you can
Yeah.
put it into the presentation mode.
Yeah.
And yeah,
Okay.
I'll just give you a 5 minutes warning.
Okay. So good morning, everyone. I am Deepan Patra. I'm a PhD student at the National Center for Radio Astrophysics, Pune, India. And my talk is about, as Divya has already mentioned, that we have developed a framework for near real-time triggered solar observation using the MWA. And I'll be talking about that. As Divya has already mentioned about the different types of solar radio emission, and he has already mentioned the solar radio burst, but let me give you a brief overview about that. So the solar radio bursts are basically spontaneous and intense, intense instances of radio emission, and they are often associated with eruptive phenomena like coronal mass ejections, solar flares, etc. And studying these radio bursts have been historically very useful, as well as they help us in understand. So basically, detecting and studying these kind of radio bursts are helpful in understanding their emission mechanisms. Also, they help us in probe the turbulent magnetized coronal medium through which the radio wave passes, and also they help us in understand the space weather research as well. However, most of these studies have been mostly focused on the dynamic spectra-based analysis. In fact, these, as you have already mentioned, the classification of the radio burst was historically done using their appearance on the dynamic spectra. However, in such dynamic spectra-based study, you do not have any spatial information of the radio burst, and so much so. However, so to have to catch these catch the nature of these kind of radio burst in their full glory, we need spectropolarimetric snapshot imaging, and for that we need radio interferometric imaging studies. So moving on, so why do we need an automated trigger in such case? So first of all, the new generation radio interferometers like the MWA, the upcoming SKLO, these are not solar dedicated, and there's a oversubscription. And also a large number of solar events are needed to be captured for a statistical study of these kind of bursts. And hence long continuous observations are not possible. And then then the telescopes have a huge data volume, and also we cannot basically predict these events beforehand. So these are transient events. So we cannot have, so basically blind observations, blind scheduling of these observations are not efficient at all. So, and on top of that, currently we are at the solar maximum. So basically, we expect more of these events to happen currently. Hence, a reliable real-time trigger can help us in improving the efficiency of capturing these solar events. However, there are some challenges. So near real time, to have a near real time trigger of these kind of events, we need access to near real time data, which can be some other solar dedicated spectrograph or some co-local station. And then we need some framework required to trigger for this trigger to be communicated to the telescope, and then the scheduling of the actual observation. On top of that, we need efficient RFI mitigation and denoising of the live data that is coming to the live data. And also the trigger needs to be raised as early as possible, because in case of these events, if you were late, then you have already missed the event. So there have been previous attempts. Um, for example, people have tried to identify radio bursts from some solar dedicated spectrograph data. However, these were all archival data. For example, Learmonth spectrograph, Lobzin and Bonin tried, and then there's E Callisto. However, these are all solar dedicated spectrograph, and these were all archival data. People in Lofer had one near real time trigger for the solar observation, where they used a burst bell method. Basically, they kept track of the total power of two sets of frequencies. One was 40 and 70 megahertz, another was 150 and 200 megahertz. And if the power of these any of the pair averaged over last 3 minutes exceeds the average by some certain threshold, they call it a burst, and they trigger their observations, and sorry, they basically dump their data. However, in this kind of scenario, you do not have the information of the extent of the whole burst kind of thing. So what we do here is we use another solar dedicated spectrograph located in Japan. It has a huge observing band from 70 to 9,000 megahertz. And also it provides a near real-time data every 2 minutes with a 2 minutes latency. And our MWA, which we use to trigger the observation, and it has a ring buffer of around 3 minutes, which with the old 128 tile system, and it can be triggered remotely. So our idea is to use near real-time data that we get from Yamagawa and use it to trigger the MWA. So basically it goes like this. So this is the Yamagawa spectrograph. We get near real-time solar dynamic spectra from this, and then we process and check whether any event is present or not, and then we send a Boolean trigger to the MWA. And this particular time diagram that you can see in the left bottom panel, it basically shows basically the data that come from the Yamagawa. The yellow block shows the data that we get from the Yamagawa, and the red block shows the data stored in the MW buffer, and the blue one is data lost due to latency. As you can see, if we use the MW buffer, we can recover most of the lost data in this scenario. So basically, this is the overview of the pipeline. We named it as STORMY, Solar Triggered Observations of Radio Bursts using MW and Yamagawa. It has three distinct steps. One is the pre-processing step, where we get the raw data from Yamagawa, and then we do band shape normalization, RFI mitigation, and some median-based denoising. And then we use this denoised data to make a binary dynamic spectra using some thresholding techniques. And on top of this binary dynamic spectra, we run our contour detection algorithm. And if any closed contour or region is detected, we call it as a successful burst detection. And this trigger is sent to the MWA. And then the buffer data is saved, and a new regular correlated observation at the frequency that we have detected the burst is scheduled. And this particular pipeline has been implemented, and it has been running from the last cycle. And basically this is how it looks in real time. So basically this is the raw data, and this is after pre-processing. It looks like this. Then we create the binary dynamic spectra, and after the feature detection we can clearly see that it has detected the burst, and according to it, it basically triggers the observation. And we have already successfully captured more than 100 radio bursts for this time range from September 2024 to February 2025. And we have also made some quick look images of some of the events that we have captured, and the rest of we are still analyzing. For example, this is one of the event that we have captured. So basically, this dynamic spectra is the denoise dynamic spectra from Yamagawa, and the top right you see the radio image that we have made from the captured data, and the bottom panel shows extreme ultraviolet maps at that particular time, and this basically shows the overlay of the radio contours on top of the extreme ultraviolet maps. Another one, this is one type 2 burst that we have captured, and it was there after a CME has occurred in this region. And the solid yellow circle shows the 2 solar radii distance, and the dotted circle shows the 1 solar radii distance, and these contours show basically the emission from the plasma, from the CME background plasma. So moving on, we have also done some performance test on our performance test using different thresholds from all the way from 3 sigma to all the way up to 20 sigma. And we have used 8,400 2-minute templates, and of which we had around 226 true events. And as you can see, and we have calculated some performance parameters called precision recall using the true positives and the false positive and false negatives. From that, we calculated the F1 score, which basically balances the precision and recall parameters. And from that, you can actually see that around 13 to 15 sigma is a kind of a sweet spot for us to balance the true positives and the false positives that we detect from the dynamic spectra. And currently, we are using 13 sigma for our pipeline.
5 minutes, Mani.
Yeah. So moving on, although we have actually developed this pipeline for triggered observation at the MWA, the framework is of general applicability. One thing we can use it for use it to find solar events, let's say in other solar dedicated spectrograph data. It can also be used in other interferometers like LOFAR or LWA or the upcoming SKLO for that matter. And also in case of the telescopes like MW and SKLO, one element itself can work as a dedicated solar monitor, and this will be much helpful than depending on a remote location, because this removes the dependency of two different systems with two different sensitivities, and it also eliminates the latency and everything, which in turn reduce the storage requirement for the ring buffer. And also, since the trigger is coming from the co-local station, it has similar sensitivity in the RFI environment, which will in turn help us reduce the false triggers that we get. And also it will help in tracking the solar activity during the other daytime observations as well. So we applied our Stormy, our pipeline to the LOFAR LBA beamform data as well, and as expected, it is working quite good. And with this, basically, I'll summarize my talk. So basically, I have shown that studying solar events in the radio frequency can provide valuable insights for both solar and heliospheric science. And these triggered solar observation can vastly increase the efficiency, as we have already captured more than 100 bursts in one semester. And our current triggering framework is yielding good results, and also enabling triggered observation using local stations will make this process less prone to latency and false triggering. Thank you.
Thank you, Deepan. Any questions?
Thanks, Deepan. That's so very interesting work and a nice demonstration. And Rigging buffer capability has been there for MWA for a long time, but although most of its use has been long shot projects like triggering on FRBs and GRBs, except maybe like the manual triggering that Bradley did to detect the intermittent pulsar. So this is great. My question to you is like, how do you decide your criteria for what sort of events to trigger? Because sounds like you might be getting like a lot of triggers from this, even from Yamagawa station. And so what sort of, how do you determine, that which frequency band to take the data, or whether you take like a multiple frequency bands to get a bigger picture of the whole solar emission?
Okay. So let me just pull it up. So basically, what we do is, you can see my pointer, right? Mouse pointer.
Yes.
Hello.
Yeah, we can see it.
Yeah, so basically, let's say we have detected some event from the Yamagawa dynamic spectra and from that, but so since we are finding some closed contours in the binary dynamic spectra, we have the frequency extent of that radio burst, let's say. Now, so first of all, whether to call it a true event or not, we are giving some sort of criteria, like it has to cover at least, let's say, 15 spectral 15 megahertz in frequency or so to be called as a um, radio burst. That is what we are currently using, but we are obviously trying to improve that condition as we go along. However, currently what we are doing is any event that is detected that has been detected has frequency, let's say, over 15 megahertz, we are considering it as a true event. And then the frequency extent that we get from the contour, from the detected contours, we are basically putting the channels in a like linear space manner within this maximum to minimum detected frequency range, and that is how we are currently observing.
Thank you. Any more questions? All right, then let's thank Deepan again.
Thank you.
Thank you, Deepan. Next, I would like to welcome Angie to tip the solar science.
Yes, hello everyone. Today I'll be talking about a couple of projects that we've been doing in the IPS group. We're going to be moving away a little bit from the sun. We're going to next to the sun. I also, to continue the trend that has been happening this week, I'm also nearly about to finish my PhD and submit, but thankfully not on the timescale of hours or days. I still have 6 weeks, so like so much time. But first I'll start off with a little bit of context in how we kind of commonly make observations of the sun and the heliosphere, like away from the radio side. And that's through a network of spacecraft that are in various orbits around Earth, the sun, Lagrange points, going out of the ecliptic, which provide very good high quality data via in situ measurements, so like particle detections made at the spacecraft, but also some imaging very close to the sun. So very high quality data, but it has very poor coverage of the heliosphere, which isn't very useful when you're trying to do large scale studies of the solar wind. You're trying to track evolution of storms through the solar wind. So you need a little bit more coverage to make that work. I'm probably not the only person in this room that doesn't want more satellites and spacecraft up there clogging up our skies. So we need to turn to other techniques of remote sensing to actually cover these gaps in the heliosphere. And one of those ways is IPS, which can technically point anywhere that you would like, as long as you can be seen from the perspective of Earth. Now, we've heard a little bit about IPS already. It's interplanetary scintillation. It's the flux density variations exhibited by compact sources caused by the disturbances that exist within the solar wind. We've seen that we can do some really great astrophysics from AJ and Nick's talks earlier this week. I don't really care about that. What I care about is the fact that if you characterize these sources, if you understand the source structure of these sources and know how they typically exhibit scintillation, how they behave, you can actually infer things about the solar wind itself, which is very useful. Now, there are two parts of the solar wind which will create scintillation, therefore you can infer back about. First is the ambient solar wind. This is just the continuous varying plasma flow that emanates from the solar surface in quotation marks. This will cause some baseline level of scintillation for every single source. And there's also the transient events that exist within the solar wind. Now, when I say transients, I don't mean like long period transients or pulsars. I'm talking about physical things moving through the heliosphere. So these could be coronal mass ejections or CMEs. These are like the solar storms that you typically think of, or they could be stream interaction regions. This is when fast solar wind rams into slow solar wind, creating shocks, accelerating particles out in the heliosphere, not quite close to the sun, quite further away from the sun, which will cause scintillation to change. The source will change in how it's scintillating as compared to the solar wind, the ambient solar wind, so you can track them through that. Now, there's a lot of different telescopes that do IPS studies. They're mostly transit telescopes. But of course, I'm here, so I, of course, use the MWA for a very specific reason, and that is the MWA is incredibly sensitive and is a wide field imaging machine, meaning we can make really good sensitive IPS observations, but because of the wide field of view, we can cover a large portion of the heliosphere with as minimal observational time on sky as possible, which is very nice. So that is why we've been taking observations pretty much every single day since 2019, when the MWA is in its extended configuration and is operational. So we have very good coverage of the solar cycle. So thank you for the last talk showing the solar cycle. So we're going all the way from minimum to maximum, taking observations right now. We're hoping, if all goes well, Stephen, if we could maybe get all the way to the next minimum would be nice, to capture the full solar cycle in IPS as well as in the solar data like we already have. When I say observations every single day, I mean we take 6 to 8 pointings around the sun. So this is the whole pointings that we can choose from. We only pick 6 or so every single day at 116 megahertz at 10 minutes. But more specifically, they have a timing integration of 0.5 seconds. It's short enough to pick up and resolve out the IPS itself, which is on about seconds timescale. We also have a comparison of what our field looks like compared to, so those inner rings are those imaging techniques that I was talking about on spacecraft, the chronographs that Divya had mentioned. So we're looking a lot further out. We're looking at about halfway, quarter of the way to Earth's orbit. So we're looking a lot further out, not at the sun, really, really far away. So kind of solar science, but it's heliophysics. So now, taking a subset of these observations that we took during 2019 and 2020, we first created a catalog of IPS sources. So these are sources, specifically GLEAM sources, that exhibit IPS. So we've now covered the full southern sky. We had data release 1 covering half of it. We have now the full sky. We even have the galactic plane and some near the galactic center, which is very exciting. And so now it's over 20,000, I should mention, quite a bit. But most importantly, they're not just identified, we've characterized them. So we know their source structure and we know how they should scintillate. We know how they behave. So now if we now measure how they're deviating away from that scintillation, we can make some inference about the solar wind, specifically the density in the solar wind. So the first thing that we did was, well, not first, one of the first things that we did was looking at the ambient solar wind. So this is looking at the shape, and it's in quotation marks, the shape of the solar wind. It was actually first discovered by IPS in the 70s and was then validated by spacecraft all the way into the 90s and now has had several other studies involved with it. And by shape, I mean the kind of equal density. If you're going away from the sun, where do you reach the kind of equal density mark? So for solar maximum, we say it's spherically symmetric. No matter what latitude you are around the sun, you will reach the same kind of density at the same radius, as you could say. But at solar minimum, we see that it's a bit of a squished ellipse. There's really fast winds coming off the poles of the sun, which lead to decreased density, so kind of giving you a squished ellipse. So there's plenty of studies that have confirmed the reduction between the equator and the pole. So it's not looking at the full solar wind, but just looking at equator and pole. Yes, there's some kind of reduction at the pole. There's only been really one study that actually looked at the shape of it, of how is it actually transitioning from equator to pole, and they gave that kind of elliptical shape. So we can do that with our MWA data. We actually have the full coverage of the latitude. This is only looking at the southern pole of the sun. The x-axis is going from, on the left-hand side, we're going from the pole to the equator. And then our y-axis is G-level. This is the deviation of scintillation that I was talking about. It's easier to understand. It's just a proxy for the density of the solar wind. We're seeing a very sharp transition. We have a gray dotted line. That's the elliptical shape. That's just above the points. We're seeing it's a really, really sharp transition from equator to pole. It's not this kind of smooth transition. It kind of looks more like an egg. It's a poorly drawn representation via Google Slides. It's a lot smoother than that, but you can see it's more dramatic than this elliptical shape. Now, this isn't just important for heliophysicists in terms of like, we like to know what the solar wind looks like. So if we're doing propagations of CMEs, it's nice to know what the density environment looks like. But this is important for other astronomy communities, like the pulsar timing. We need to know what the solar wind looks like. There needs to be some kind of model of the solar wind at any point to take into account for RM and DM measurements, which is very precise. We need to know exactly what those changes are, especially if we have pulsars going really close to the sun. Now, there could be reasons why there's a difference in shape. All of the studies I've been talking about, every single one was taken at a completely different solar cycle. So maybe it's solar cycle dependent. Maybe solar cycles are unique to each other in how they form their solar wind, depending on the coronal hole distribution. Or it could also have a dependence on the solar elongation. Like I was saying, we're a lot further away from the sun. The majority of these studies were done much closer to the sun. Where the furthest out, potentially the density environment changes when you go really far out. So it's a little bit more work needs to go in on the same solar cycle at different solar elongations would be the most ideal. So yes, that's the ambient solar wind. So now we'll move on to the more exciting thing, I would say. I like the ambient solar wind, but most people like the storms that exist within the solar wind more. So this was more of a project that was trying to validate or compare the IPS observations compared to kind of these commonly used techniques. So these spacecraft and these remote imaging that these spacecraft do. So this was kind of creating like a confusion matrix of like, what are they seeing that we're not seeing? What are we seeing that they're seeing and they're not seeing? And the first was just to collect a bunch of catalogs. So we have 3 catalogs. The first 2 are CME catalogs based on the remote imaging that I was talking about very close to the sun. One's manual, one's automated. If you want to hear my discourse about the difference between them, you can talk to me afterwards. But they only look at CMEs because you can image CMEs, but you can't image stream interaction regions. whilst the third catalog is a combination. It's CMEs and stream interaction regions, and it's built upon the identification of in situ measurements of a spacecraft. So this spacecraft stereo sits at 1 AU, it's in the ecliptic plane, and it's just measuring pretty much a time series of different values of density, of velocity, and that's how we determine whether something's a CME or a stream interaction region. So then what I did was, for about a 7-month period in 2019, I took all of the events that they saw in those catalogs and saw, do we see them in our IPS observations? And good news, 84% of the events had data available, which is very pleasing to see. The fact that we've got pretty good coverage of the heliosphere in terms of like temporal coverage for an instrument that can only be observing for half of the day. It still is being able to capture 84% of the events, just purely because of how wide the field of view is. Things remain in the field of view for quite some time. Now, 68% of those events, so 68% of the 84 catalogued events, had a potential match in our observations, meaning we have captured something in our field of view that could potentially line up with the catalogued event. With our strongest cross-match with that stereo catalog, with that catalog that's not just looking at CMEs, but also stream interaction regions. Isn't surprising, both of these features will create density enhancements that IPS can see. So it makes sense that we would cross-match with the catalog that shows both, not just one of them. So then this poses the question of, let's just compare the IPS to catalog. So this was first identifying features in the our observations ourselves, and then seeing if those features matched with an event from the catalogs, pretty much. And yeah, we see that it do. Yeah, 53% of the time, yes, something that we see in our IPS observations, they see in the catalog. We can match with the catalog. It's pretty good. It's more than half, but that is still quite a large percentage that doesn't have a match. And what's interesting about this 47% is the majority of these were sitting well out of the ecliptic plane. So more than 10 degrees away from where these spacecraft usually, or like the Earth, the spacecraft actually operate. And if we remember, the majority of our cross-match from our last analysis was with that spacecraft. It was with something that was in the ecliptic plane. So if we're seeing things that are not even going to be able to be detected by this spacecraft, so of course we don't have as much of a match. This could also potentially pose that we're seeing a lot of stream interaction regions that the CME catalogs can't see, because the CME, we can capture really close to the sun, but stream interaction regions, they're only in outer heliosphere, and we're not capturing these through the lack of spacecraft. So this is one of these events. I've talked about it before at many different conferences. So that proxy for density is the color bar now. So more red means higher density, usually meaning that there's a feature in the solar wind. And that little red square on the left, that's stereo. That's the spacecraft that we compare our catalogs, our events with. And you can see our like two little arcs, our two little features are traveling right below stereo. Stereo is not going to be able to see them. It's not going to be able to detect them since it's only a small little spacecraft. But what's exciting as well about these IPS observations is not that we're identifying events that are out of the ecliptic, but we're also seeing them in unprecedented detail. We're not looking at just a time series. We're not just looking at just the velocity or just the density. We actually get to see what these features look like. They have angular structure. We can see two little shocks in the heliosphere and measure them and characterize them and watch them evolve as well, which is the exciting thing. So IPS, great. MWA IPS, even better. Since this is a project meeting about the launch of phase 3, very exciting. I thought I would have a little bit more of a look to the future. So with the MWA data, we still want to process and get our hands on the true solar maximum data as well. Compare and contrast, there's going to be a lot of events in that maximum data, as well as the ramp down phase and the ramp up phase. So the transition regions, they behave differently. So that's exciting things to come. We also have ASCAP on board as well now, which kind of covers the ring in between the images. So that's what the spacecraft images look like, those coronagraphs, that blue image there. The MWA observations are out in the heliosphere, and ASCAP covers beautifully, so we can then maybe track features all the way from coronagraphs into ASCAP into MWA, which would be very exciting. And of course, always SKA, we have an increasing collecting area, meaning we can go fainter, meaning we can get even more degree level accuracy on these features as well. But I wouldn't write off the MWA because it's truly doing, I would say, some really great work. And with that, I'll leave you all. Yeah.
Thank you, Angie. So any questions?
Really cool talk. Good luck for the final 6 weeks. So just your second last slide, not your summary one, but the one where you were showing that structure. Yeah. How common are these sort of arcs? Do you see that as a very common feature of these interactions?
Yeah.
And is it always arcs, or are there different types of structures?
Sometimes they look more blobby, but usually they're arc-like shaped. This isn't really surprising because we assume that these density features are like shocks in the heliosphere. So you would assume would take more of an arc-like shape. So depending on the geometry, they might look more arc-like or more blobby. But yeah, most of the time they're usually kind of arcs.
And like multiple arcs, or usually just the one? Like
Sometimes there's one, sometimes there's multiple.
more data
Sometimes it's
needed?
the whole field of view. Like it depends.
Cool. Thank you.
Thanks, Angie. Beautiful talk here. You said that these various IPS sources you have also been characterizing, right?
Yes.
Right. Yeah. So, do you also characterize their sort of departure from circular symmetry? I mean, or not so much? Yeah.
I don't know. I'm actually not sure. That might be a John question. John is in the audience. I'm more of the flux density deviation gal.
Sure. Thanks. Yeah.
Yeah, we currently just characterize an individual source's IPS by its normalized scintillation index. It's difficult to go much beyond that apart from the very, very brightest sources, because it's sort of a little bit degenerate with the latitude from which the solar wind is emanating. So as you probe different angles with different velocity vectors across the source, you're also looking at different latitudes. So yeah, it's quite tricky to go beyond that sort of single number which characterizes the source structure. We are looking at it at the very brightest sources.
Any more questions? Ron?
In your introduction, you mentioned knowing the shape of the heliosphere could matter for people doing pulsar timing to look for primordial gravitational wave events. So now you have shown that their simple spherically symmetric model is wrong. Are you having any influence on that community to get them to use more sophisticated models?
Me personally, I have only a small access to pulsar scientists, and I'm spreading the word in that aspect. But in terms of IPS, there is influence. We've been doing some studies. I can't remember what university the PhD student is from. But in terms of using IPS to inform some kind of model and then seeing if that is actually making an improvement to these RMDM, I can't remember which one, measurements. So not me personally, but yes, in terms of the community and MWA IPS observations and other observations made by the group in Japan, yes.
Oh, Ramesh?
Not a question, but I just wanted to comment, trying to answer Ron's question. Yes, it is a fact that at least definitely after this recent PTA results and the community at large is recognizing that solar wind is something that we definitely need a better model, particularly for from a PTA context. But it's great to see that, that this is the kind of model that is coming out of solar investigations or IPS investigations. But The way to convince a pulsar community would be actually to have those regular measurements and trying to build a timing model or the solar wind model into packages like Tempo2 and Pint and other things. And they have to be convinced that, okay, using this gives us like a better precision on those pulsars in and around the galactic ecliptic plane. So that is like a task. And I think that is another reason why I would, again, advocate instruments like MWA getting into this monitoring kind of a projects and build up this database, because like Angie says, we have the capability, MWA, to make those precision measurements. So if at all, you know, that pulsar community, timing array community is trying to get a better model, this will be like an incredibly useful measurements to go into that modeling work.
Hi, Angie. Thanks for that talk. It was really interesting. I was just wondering, I don't think it was explicitly said, but with phase 3 coming on board and the ability to go to 256 tiles, lots of long baselines for you, are you planning on utilizing the whole 256 T array, or do you have a specific phase 3 or this semester array config in mind for new observations?
For now, we're still using the 128 as if it was the extended configuration that we have, because it's the long baselines that really matter for us rather than the small baselines. In theory, we could move up to 256. I don't know what the payoff is in terms of, do we get more information out from those shorter baselines compared to now we're doubling our storage on the system, and or we'll just then increase the timing to do imaging and increase the timing of the reduction of things, when in theory we would like to get these observations through as quickly as possible for like simulations or for monitoring of CMEs and things like that. So maybe John has specific plans in mind for 256, but for me, I'm happy with 128.
Right. Let's thank Angie again. Thanks a lot. And then the next one is going to be an online presentation again from Pooja Maji about a detailed polarimetric study of type 2 solar radio bursts with MWA.
Yeah.
Hi. Just give me a second. Let me. All right. Could you please share your screen and present it in Teams?
Yeah, sure. Yeah, can you see my screen?
Yes, we can see your screen, and I will give you a 5 minutes warning.
Yeah, sure. Good morning, everyone. I am Pooja Maji, and I am a PhD student working with Divya Oberoi. And today I'll be presenting our work on a detailed polarimetric study of a type 2 solar radio burst using MWA. So what are these type 2 solar radio bursts? So you may have heard a lot about CMEs, which are the potent driver of space weather. So when these CMEs erupts, they often drive a shock, and these shocks give rise to these plasma emissions, which are known as this type 2 radio burst at a frequency which is at the local plasma frequency, and it's harmonic. So here this figure basically shows you the dynamic spectrum. So this is how the type 2 emission looks like. So this is the fundamental emission, which is at the local plasma frequency, and this is the harmonic emission. And as you can see here, there's a drift, and which is coming because as the shock propagates through the coronal medium, it basically encounters lower and lower density region, and hence lower and lower plasma frequencies, and therefore you can see the drift in the emission. So now, why the polarimetric properties of these type 2s are important? That is because the geoeffectiveness of the CMEs are governed by the CME entrant magnetic field, and as well as its interaction with the local ambient magnetic field, and therefore it is very important to understand the local magnetic field. And the polarimetric properties of type 2s can be used as a remote sensing observational probe to understand this CME entrant magnetic field. And especially the harmonic emission is very, very important because it is expected to have a very minimal propagation effects. And in the past, there are several studies where polarimetric properties of type 2s has been used to estimate the magnetic field strength. And apart from that, these polarimetric properties can also provide the information about the shock strength, ambient plasma medium properties, and so on. And not only that, it can give you, it can provide the insights about the underlying emission mechanism, and as I said, the propagation effects as well. So what do we know so far about this type 2 polarimetric properties of this type 2 emissions? So in the literature, there are diverse reports about the polarization properties, which ranges from unpolarized or weakly polarized to very, very strong polarization, which can goes up to 70%. And so there are several reports which says that the harmonic emission shows weaker polarization. However, there are also reports which tells the inverse of it. But however, there are reports which has found that the fine structures are more polarized than the burst continuum itself. But an interesting thing to notice is that there are no linear polarization has been reported so far from this type 2 emissions. But it is very recently where a detection of linear polarization has been reported from other other types of radio burst using MWA by They et al. Now, a very interesting point is that vast majority of this existing type 2 polarization studies are based on the dynamic spectrum. Now, dynamic spectrum can give you only spatially integrated information, where the polarization emission can both be positive and negative. And if you are getting an integrated information, you are basically missing out a lot of information about the properties. And therefore, to study these type 2 emissions, it's very important to do imaging studies. And as from the dynamic spectrum, you must have seen that there are a lot of variation in the emission. So these show a lot of variability in time and frequencies, and therefore a very snapshot images with a very small frequency resolution imaging studies is very, very important to study to study the type 2 polarization properties. And for that, we have carried out a detailed polarimetric study using MWA. And the reason behind is that MWA is intrinsically capable of giving high fidelity images even within a very small time and frequency resolution. So here let's talk about the type 2 event. So this is an event. So this is the type 2 event. So this is the dynamic spectrum of the type 2 event. And this was captured by Learmont spectrograph on 28 September 2014, which the time where MWA was in phase 1 mode. And as you can see here that, so this is the harmonic emission and this is the fundamental emission. And these rectangular boxes are basically the 6 spectral bands in which MWA has observed this type 2 emission. And the lower plot basically shows you the same dynamic spectrum, but here each of these spectral bands has been shown. So we have made full stroke snapshot images with a time interval of with a time resolution of 0.5 second and a frequency resolution of 160 kilohertz using Paircast and the recent modifications that you can get and look from the Day et al. Paper. So Here are the full Stokes images of this type 2 event. So this is the Stokes I, Q, U, and V images. And this is the red circle is basically the optical sun, and this is the type 2 emission. And as you can see here, the type 2 emission shows a very high signal to noise ratio emissions at Q, U, and V maps as well. And if you look at the V maps, Q, U, and V maps, you can see another source which is coming from another active region which was present at that time. So using the Q and U maps, we have generated the linearly polarized intensity maps and as well as the polarization angle maps. So in a study, we find that we studied the morphology of this type 2 emission with time and frequency. So here this plot shows, so these are the Stokes I, Q, U, and V images with a time interval of 10 seconds, and this dashed line basically shows the cut over which these images are shown. So as you can see here, if you look at the while the Stokes I image shows no morphological changes over the time, but if you look into the Q, U, and V images, you can see that there are a lot of things happening in these images. So if you look at the Stokes V images, the last column, you can see that initially there were two polarity sources where the positive polarity was not that evident, and then later on it becomes evident, and then after that it again become into the negative polarity source. And then if you look at the Q and U sources, you would find that with time the polarity of both the sources changes. So it basically shows that the source morphology as well as the polarity of the source in the Stokes QUV images changes across time within the 10 second, even less than 10 seconds as well. But one thing to notice is that if you look at the Stokes V images, you would find that the location of these positive and negative sources are consistent over time. Now we did the same exercise to look at the morphological source morphologies with frequency. How does that change with frequency? So as you can see here, that in this case as well, the Stokes Q, U, and V images shows a lot of frequency changes over frequencies. However, in this case, the location of different polarity sources are not consistent across time, and the reason can be that because they are coming from different part of the shock as they are of different frequencies. So now from that we characterize these sources, and we found that for this type 2 burst we found a weak circular polarization of up to 5%, and for the first time we detected linear polarization from a type 2 burst which can go up to 9%. Now we wanted to study the spectral and temporal variability of the polarization fractions both for the circular and linear. So here this is a plot which shows the the temporal variation of the polarization fraction. So this is for the Stokes I source. This is for the negative polarity Stokes V source, the polarization fraction, and the polarization fraction for the positive polarity V source. And as you can see here, so these are the two colors are basically the nearby frequencies, which you can see here. So these are the two lines representing the two the two frequency stamps. And as you can see here that the nearby frequencies, the temporal variation at the nearby frequencies are correlated, and there are a lot of emission in case of the for the negative polarity sources, and while there are the positive polarity sources is not always present. And also if you can see here that there are a lot of rapid fluctuation at a very small time scale, even within half a second, which basically tells you that there are a lot of, whenever the emission was passing through the coronal medium, it was passing through a lot of small scale inhomogeneities or coronal densities. So now to look at the spectral variation. So these are the spectral variations at two nearby times, which are which are different by 10 seconds. So these are the two lines which are representing the two timestamps, and these are at the shaded regions are at different spectral bands. And you can see here that the nearby frequency shows a similar kind of similar polarization fraction, whereas if you look at the nearby times, their variations are not correlated or are not similar. So it's basically the correlation in spectral variation drops with time. Now we did the same with the linear polarization fraction as well. So this is again the Stokes I image, Stokes I emission, the temporal variation of the Stokes I emission, and this is for the linearly polarized fraction. And as you can see here as well, the nearby frequencies are, the variation at nearby frequencies are correlated, whereas there are a lot of rapid fluctuations at small time scales, which again says the same thing, that they are the emission, both circular and polarized emission, both are going through a lot of inhomogeneities. Now, interestingly, for this case, when we looked into the spectral variations at a very close by times of 10 seconds interval, and here we can see that the variations at the two timestamps are quite similar, and also quite similar, and also here as well you can see that the nearby frequencies are correlated to each other, which basically tells you that whatever is giving rise to this linear polarization emission, the structure is very stable across time, and also it is large because this similarity you can see is consistent for all of the spectral bands. Then to look deeper into it, we also looked into the polarization angles, and here these are the polarization angles map. So this is the polarization angle across, so this is the polarization angle with the polarization fraction, linear polarization fraction, and this is the polarization angle with the linear polarization absolute flux. And here as you can see that the different color are showing different frequencies, and you can see that at different bands the linear polarization the polarization angles are very consistent. And also in the lower plot you can see that the polarized emission with high polarized absolute flux are always sustaining a particular polarization angles, which again tells you that the magnetic structure through which this emission is passing through is very stable. So now to conclude my talk, so detailed polarimetric imaging, snapshot imaging studies are very important, and they can, as you have already seen, that they can reveal a lot of feature which was previously unobserved or unappreciated, whether dynamic spectrum only can not provide you that. For this particular event, we found a dominant left-handed weakly circularly polarized emission, which goes up to 5%. And the evolution in the Stokes V maps shows that there are significant propagation effects, there are polarization inversion, and this is the first time when we found a linear polarization from a type 2 solar radio burst, which can goes up to 9%. And as you have already seen that the temporal variations as well as the polarization angles across different frequencies are very consistent, which basically tells you there is a very large and stable magnetic field structure during this event. And also our expectation that the harmonic emission would have a very less propagation effect may not be correct, because here we can see a lot of propagation effect even in the harmonic emission as well. So with that, thank you so much.
Thank you, Pooja. Any questions?
Hi, Pooja. Can you hear me?
Yeah, I can.
Yeah, Bornali here. So very nice talk and very exciting stuff. So I was just curious about, so now that you have found linear polarization and circular polarization as well. So what does it imply about the scenario of type 2 burst production? And also I was curious about, is it a special burst? Like, is it the only burst that has been studied in that great detail, or is it like now you expect that now that you have this more sophisticated tools, would you expect to see this level of polarization for all type 2 bursts? Or yeah, that's kind of what I was curious about. Thanks.
Yeah, thank you. So, okay, so to answer the second part of your question, that yes, so this is the first time when such a detailed polarimetric study of a type 2 burst has been done, and therefore this is the only one for which we have so far have done this analysis. I am planning to do the same for other type 2 burst as well, and I do believe that this is not a very special burst and it is very common, and we are right now getting it just because we have a better analysis, like we are doing a better analysis, while in the recent paper by Shoham Day et al. So in that paper as well, they have found linear polarization from other radio emission, and which with other active emission, which kind of now I have started to believe that this is not very unique. This is very common in radio emission. It's just we have not looked into great details. And yeah, sorry, what was the first part?
So what does this new findings imply about the scenario leading to this type 2 burst production? So,
yeah, thank you. So talking about that, so we think that this is coming from the propagation. This is mostly coming from the propagation effect, and if it is true that there are understanding or our assumption that okay, using the harmonic emission, harmonic emissions can be direct probe to the magnetic field, that is no longer true. So that we have to take care. So no, I mean, take care with more attention. And also when we say that the scattering or the propagation effects are very, very less for the harmonic emission, which is not true, whatever we see here as well. So yeah, does it answer your question?
Yeah, thanks.
Yeah.
Yeah, we can have one last question if anyone has any. All right. Thank you, Pooja, and let's thanks Pooja again and all the presenters.
Thank you.
And